Have you ever wondered how a machine learning model, after seeing only a limited amount of data, can still make surprisingly accurate predictions about things it has never encountered before? It is not magic. It relies on a fundamental concept. Understanding inductive bias is absolutely critical for machine learning models because it dictates how a model generalizes from the data it has seen to make predictions on new, unseen data. It essentially defines the model's fundamental learning strategy and its built-in assumptions about the underlying patterns in your information. At its heart, inductive bias refers to the set of assumptions that a learning algorithm makes to predict outputs for inputs it has not explicitly been trained on. Without these assumptions, a model would have no basis for extending its knowledge beyond the exact training examples. For instance, a linear regression model assumes a linear relationship between features and target. A decision tree might assume hierarchical conditional relationships. These biases are essential because, as described by the no free lunch theorem, no single algorithm is universally superior across all possible problems. The bias helps the model find a specific, plausible solution among countless possibilities, guiding it towards patterns rather than simply memorizing data. Knowing about inductive bias provides you with powerful insights for practical model development. It helps you intelligently choose the right algorithm for your specific problem. If you suspect your data has a smooth, continuous underlying pattern, a model with a smoothness bias, like a support vector machine or a Gaussian process, might be a good fit. Conversely, for data with clear, distinct categories, a decision tree or a random forest could be more appropriate. This understanding also assists in hyperparameter tuning, where you adjust the model's complexity to align with your data's expected bias, preventing issues like underfitting or overfitting. Beyond just choosing a model, grasping inductive bias allows you to interpret why a model makes certain predictions and diagnose when it might fail. For example, if a model with a strong linearity bias performs poorly on inherently nonlinear data, you can pinpoint the mismatch between the model's assumptions and the true data structure. This deeper insight helps you design more effective feature engineering strategies or consider ensemble methods that combine models with different inductive biases to achieve better robustness. Ultimately, a conscious and informed understanding of inductive bias moves you beyond simply applying off-the-shelf algorithms. It empowers you to build machine learning systems that are not only more accurate but also more robust, interpretable, and specifically tailored to the unique characteristics of your data and problem domain. It transforms you from a user of tools into a skilled architect of intelligent solutions.